Yes.
How is it useful for us, sir, if a process is stationary?
So now I think if you go back to Sumit's question, now see the covariance depends on the difference, right? The mean is the same. So now this leads to the following result. Okay, so let me write it as a result. If you want to be very formal, you can write it as a theorem. So a Gaussian process okay x of t belonging to some set tau is stationary. Okay, it's both ways if and only if expected value of x of t is equal to expected value of x of 0. Okay, so this is for all t, and the covariance of this kx of t comma t plus u, this depends only on u, the difference, right? This is true for all u and t belonging to t. Is that fine? So why if and only if? That's because if the distributions match for a Gaussian process, essentially the mean and covariance should match. That's all. So that's why it's if and only if, right? If these two match, let's say the mean, this equation is valid, and the covariance, it depends on the difference. That means the distribution, the entire distribution doesn't, it only depends on the difference, right? It should not depend on the absolute, the time at which you are going to sample, right? So what is the use of this? Well, now you can specify the whole Gaussian process by one mean, right? And a covariance function which depends only on one parameter. Do you agree? You agree with this?
Yes, sir.
Huh? So, as opposed to a general Gaussian process where you need to specify the mean at every time instance, in other words, you need to have uncountably many means and uncountably many covariances of two variables. Now it boils down to just one mean and one covariance function, that too in one parameter, right, or one variable. So, which is a significant reduction of the number of parameters you need to describe the Gaussian process. So in other words, stationary process is a very simple Gaussian process, simple to describe and easy to work with, because if you want to understand the this particular stationary Gaussian process, you need to know the mean and the covariance function. That's all. For a general Gaussian process, you need to know the mean at every instant, which is impractical. I mean, you cannot find the means at every instant, and the covariance function, which is again very hard. Is this okay? Any questions?
Sir,
Yes.
if it's stationary, higher moments also will be same, sir.
Yes,
Means
it doesn't depend on, for example, expected value of x square of t is same as expected value of x square of 0.
Yes, sir.
So, yes,
Yes, so in this case, sir, we can calculate any of at any instant of t, no, sir. Then we can.
exactly. So,
Yeah.
if you look at Gaussian, right, how do you write the higher order movements? For example, the third moment will be 0, right? Because if it's a third central moment, meaning expected value of x of t minus mu whole cubed will be 0, right? Because of symmetry. All the even moments, I can write it as a function of first and second moment, right? So that means, so if you take, for example, two random variables, right? So if you have this process at time t and let's say at time t plus tau, so the difference is tau. Now, if you look at any joint moment of these two, right? So the cross covariance, whatever you want to call it, so it depends only on tau because the whole distribution depends only on the difference, not on the absolute time instant at which you are going to sample, right? Is that clear?
Yes, sir.
Hmm?
Yes,
yes,
sir.
sir.
So
Okay.